Last episode, you built the forward pass of a two-layer MLP in pure NumPy. You can now compute an output from any input. But the output is wrong because the weights are random. Today we fix that.
Backpropagation is the algorithm that computes how much every single weight contributed to the error, so gradient descent can nudge each one in the right direction. It is the reason deep learning works. I'm Mahaz. By the end of this episode, you will have derived backprop from the chain rule, implemented a complete backward pass in NumPy, and verified it with a numerical gradient check. Today, loss surface, gradient descent, the chain rule, the backward pass derived layer by layer, weight update rule, full NumPy implementation, gradient check, and one complete training step. Before backprop, you need to picture what we're minimizing, the loss surface. Every set of weights defines a point in parameter space. At each point, the loss function gives you a number, how wrong the network is. Imagine a hilly landscape. Peaks are high loss, valleys are low loss. Training is finding the lowest valley. For a network with millions of parameters, this landscape is in millions of dimensions, impossible to visualize. But the math works the same way. At any point, the gradient tells you which direction is uphill. Go in the opposite direction of the gradient, downhill, and you reduce the loss. Do this repeatedly, and you approach a minimum. This is gradient descent. The gradient is the key.
The question backprop answers. Given the current weights and the current loss, what is the gradient of the loss with respect to every weight? Computing that gradient efficiently is the entire problem.
Gradient descent, the optimization algorithm that uses the gradient to update weights.
The update rule. New weight equals old weight minus learning rate times the gradient of the loss with respect to that weight. The minus sign. The gradient points uphill, so we subtract it to go downhill. The learning rate controls step size. Too large, you overshoot the minimum and the loss oscillates or diverges. Too small, training is very slow. Typical starting values, 0.01 or 0.001. The weight update is applied to every single parameter. Every entry in W1, B1, W2, B2. For a network with 1 million parameters, that's 1 million gradient values to compute. Backprop makes this tractable. One pass through the dataset computing gradients and updating weights is one epoch. You repeat for many epochs until the loss converges, or until you run out of time or compute.
Why do we need backpropagation specifically? Why not just estimate gradients numerically?
The naive approach. Perturb each weight by a tiny epsilon. Run the forward pass. See how the loss changes. Divide by epsilon. That's the numerical gradient. It works, but it requires 2 forward passes per weight. 1 million weights, 2 million forward passes per update. Backpropagation computes the gradient of every weight in a single backward pass, the same cost as 1 forward pass. For 1 million parameters, 1 backward pass, not 2 million forward passes. That's the efficiency gain. The insight, the chain rule lets you reuse intermediate computations. Instead of computing each gradient independently, you compute gradients from output to input, reusing results at each step. This is dynamic programming applied to differentiation. Backprop was not new math. The chain rule has existed for centuries. What was new in 1986, when Rumelhart, Hinton, and Williams published it in Nature, was the realization that you could apply it efficiently to layered networks.
The chain rule. One equation. The entire foundation of backprop.
If y depends on you, and u depends on x, then the derivative of y with respect to x equals the derivative of y with respect to u, times the derivative of u with respect to x. In symbols, dy over dx equals dy over do times do over dx. For a neural network, the loss L depends on Z2, which depends on A1, which depends on Z1, which depends on W1. The gradient of L with respect to W1 is the product of 4 derivatives chained together. Written out, partial L over partial W1 equals partial L over partial Z2, times partial Z2 over partial A1, times partial A1 over partial Z1, times partial Z1 over partial W1. Each of these partial derivatives is simple to compute individually. This is why we stored Z1 and A1 during the forward pass. We need them to compute the local derivatives at each layer during the backward pass.
Quick review of what the forward pass stored, and why each value matters for backprop.
z1 equals w1 times x plus b1. We stored z1 because the derivative of real u depends on whether z1 was positive or negative. Specifically, real u prime of z is 1 if z is greater than 0 and 0 otherwise. a1 equals real u of z1. We stored a1 because the gradient of the loss with respect to w2 involves a1. It appears in the weight gradient formula for layer 2. z2 equals w2 times a1 plus b2. This is the raw output. For MSE loss, the output is z2 directly. For cross-entropy, the loss is computed from z2 through softmax. Either way, this is where the backward pass starts. The golden rule: store everything you need for the backward pass during the forward pass. If you try to recompute it during backward, you've already lost the intermediate values.
Now the derivation. Starting at the output, working backwards.
We use MSE loss. L equals 1/2 times the mean of y hat minus y squared. The 1/2 is a convenience that cancels the 2 from the derivative. Partial L over partial z2 equals y hat minus y, the prediction error. This is delta 2. Delta 2 is shape b by n_out, one error value per output neuron per example in the batch. For a batch of 4 examples with 2 output neurons, delta 2 is shape 4 by 2. The gradient of the loss with respect to W2 is delta 2 transposed times A1, divided by batch size. The gradient with respect to B2 is the mean of delta 2 across the batch dimension. These are the exact formulas you implement in code. dW2 equals delta 2 transposed at A1, divided by B. dB2 equals the mean of delta 2 over axis 0. Clean matrix operations, no loops needed.
Now propagate the error back through the hidden layer.
To get the gradient at layer 1, we need to know how much each hidden neuron contributed to the output error. We propagate delta 2 backward through W2. Delta 1 equals delta 2 times W2, element-wise multiplied by the real u derivative at Z1. The real u derivative is the heaviside step function, 1 where Z1 was positive, 0 where Z1 was negative or 0. In number py, written as Z1 greater than 0. This masks out the neurons that were inactive, their gradient is 0, they didn't contribute. So, delta 1 equals open paren delta 2 at W2, close paren, element-wise multiplied by open paren Z1 greater than 0, close paren. Delta 1 is shape b by n_. Then dW1 equals delta 1 transposed at x, divided by b. dB1 equals mean of delta 1 over axis 0. This pattern extends to any number of layers. For each layer from output to input, propagate delta backward through the weight matrix, multiply by the activation derivative, then compute the weight gradient.
The weight update, the final step that actually changes the parameters.
After computing dW1, dB1, dW2, dB2 from the backward pass, apply gradient descent. W1 minus equals learning rate times dW1. B1 minus equals learning rate times dB1. Same for W2 and B2. The minus sign is critical. The gradient points in the direction of steepest increase in loss. We subtract it to decrease the loss. If dW1 is positive for some weight, that weight gets reduced. If negative, it gets increased. The learning rate scales the step. Too large, weights overshoot the minimum. Loss oscillates wildly or diverges. Too small, training converges but takes forever. Start with 0.01. Reduce by 10x if loss diverges. After the update, the weights are slightly better than before. Run the forward pass again with the new weights. The loss will be slightly lower. Repeat thousands of times. That's training.
Now the code. Adding the backward method to our MLP class from episode 9.
The backward method takes y true, the target labels. Step 1. Output delta. Delta 2 equals Z2 minus y true, divided by batch size. Step 2. Weight gradients for layer 2. dW2 equals delta 2 transposed at A1. dB2 equals sum of delta 2 over axis 0. Step 3. Propagate delta to layer 1. Delta 1 equals delta 2 at W2, element-wise multiplied by Z1 greater than 0,
the ReLU mask. Step 4. Weight gradients for layer 1. dw1 equals delta 1 transposed at x. db1 equals sum of delta 1 over axis 0. Step 5. The update. w2 minus equals lr times dw2. b2 minus equals lr times db2. w1 minus equals lr times dw1. b1 minus equals lr times db1. That's the entire backward pass, 10 lines of NumPy.
To train, for each epoch, call forward of x, compute the loss, call backward of y true. The weights update automatically. Print the loss every 100 epochs to watch it decrease.
How do you know your backprop is correct? The numerical gradient check.
For each weight in W1, perturb it by plus epsilon, run the forward pass, record the loss. Perturb by minus epsilon, run again. Numerical gradient equals loss plus minus loss minus, divided by 2 times epsilon. Use epsilon equals 1 times 10 to the power of negative 5. Compare the numerical gradient to your analytic gradient from backprop. They should match to about 7 decimal places. If they don't, your backward pass has a bug. The relative error formula, absolute value of analytic minus numerical, divided by maximum of absolute values. If this is less than 1 times 10 to the power of negative 5 for all weights, your backprop is correct. If it's larger, find the layer that's wrong and rederive. Run the gradient check once after implementing backward. Not every training step, it's too slow. Once you've confirmed correctness, remove the check and train normally. This is standard practice in DL research.
Let's put it all together. One complete training step.
Step 1. Forward pass. Call MLP.forward of x. The network computes Z1, A1, Z2, and returns the output. Step 2. Compute the loss. For MSE, 0.5 times mean of Z2 minus y squared. Step 3. Backward pass. Call MLP.backward of x, y, LR. Deltas are computed, weight gradients are computed, and all 4 weight matrices are updated in place. Step 4. Log the loss. Every 100 steps, print the current loss value. You should see it decrease steadily. If it increases or oscillates, reduce the learning rate. If it plateaus immediately, check your gradient formulas. Run this loop for 1,000 epochs on a simple dataset. XOR, for example. Watch the loss go from about 0.25 down towards 0. The weights are learning. That's the entire training loop. Everything else is details.
Before episode 11, 6 checks.
Check 1. You can explain what the loss surface is and why gradient descent finds a minimum. Check 2. You can state why backprop is more efficient than numerical differentiation. Check 3. You can apply the chain rule to a 2-layer network and write out all 4 partial derivative terms. Check 4. You know the formula for delta 2, y hat minus y, and why it starts the backward pass. Check 5. You can derive delta 1 from delta 2 times w2, multiplied by the ReLU mask. Check 6. You can implement the full backward pass in NumPy from memory and run a gradient check. 6 checks. All pass. Episode 11 awaits. Loss functions deep dive. MSE, cross entropy, BCE, and when to use each one.
Recap. What backpropagation actually is.
Loss surface, parameter space landscape. Gradient descent. Subtract gradient times learning rate from weights. Chain rule. Del L slash del W1 equals del L slash del Z2 del Z2 slash del L1 del L1 slash del Z L1 slash del W1. Backprop computes this in one backward pass.
Delta 2 equals y minus y. Delta 1 equals delta 2 at W2 times Z10. dw equals delta at input slash b. db equals mean delta. W dash equals LR times dw.
Your challenge. Add backward to your EP09 MLP. Run a gradient check. Post the max relative error. Backpropagation is not magic. It is the chain rule applied systematically from output to input, reusing intermediate results at each step. That's it. That's the whole algorithm.
Every framework, PyTorch, TensorFlow, JX, is doing exactly this under the hood. Now you know what's happening when you call loss.backward.
Next episode, loss functions. MSE, cross entropy, BCE. What each one assumes about your data, and when to reach for each one.
Subscribe. Run your gradient check. See you in episode 11.